Hi, I'm Jake Walter. I'm the state seismologist at the Oklahoma Geological Survey. Today, I'd like to tell you about the Python package that we've developed at OGS called easyQuake, which is a turnkey machine learning driven earthquake identifier and locator tool. And I'd like to acknowledge all my co-authors and staff at OGS who help keep the network running and detecting earthquakes. And this easyQuake package helps us do that mission, complete that mission to a greater degree. So we want to identify as seismologists whether we're engaged in sort of the observatory end of seismology or the basic research driven oriented seismology. We want to identify the smallest earthquakes because it helps us validate our models for stress and how stress acts upon faults to promote slip. And then that slip can, obviously produce earthquakes, whether that's microseismicity or slip in large damaging earthquakes. And so whether that's poor pressure driving or poor elastic stresses, we'd like to understand those, and detecting small earthquakes helps us understand the earthquake physics. So we developed this package which combines machine learning driven picker developed by Zach Ross and colleagues at Caltech with a Python 1D associator from Chen and Hall in 2016. And that associator also, while it aggregates picks and identifies possible event times, it also completes a grid search on a 1D velocity model to identify possible locations for that seismicity. Finally, we compute the magnitudes. Given that preliminary location, we can come up with an estimate for the earthquake magnitude, and then we want to do something else with that data. So easyQuake provides a fully QuakeML compatible catalog and an individual QuakeML files as output to then go take it to, say, HypoDD or hash. And we even include submodules which actually will output those types of driver files for external relocation programs. And it's flexible enough to be run on either data collected already, or you can direct it to download data from FDSN servers. So the machine learning component of that takes millions of seismograms from Southern California, and this is Zach Ross's work, to train a fully connected neural network, and which outputs on new data. It'll detect probabilities of P and S pick times on 3-component data sets. So you feed it new data and it'll come up with these probabilities. And you can use that hyperparameter to sort of tune what level of confidence you want in that detector's ability to produce positive identifiable P and S picks. So when we implement it into our routine operations, we use it in a way that sort of augments our real-time ability to detect and locate and provide event updates. So the open circles are the routine system, the real-time system, SeisComp3, and then the closed circles, the black circles, are the machine learning or easyQuake augmented earthquake detections in our catalog. And you can see from this Gutenberg Richter plot that we improve the catalog completeness by something on the order of 0.7 magnitude units by augmenting this our routine operations with easyQuake. Here's an example of an event that would have gone undetected if it weren't for easyQuake augmenting our real-time detection methodologies. So this is a magnitude 0.7 earthquake, which was barely discernible on some of these more distant stations. So you can sort of qualitatively see how easyQuake helps us detect events that would have otherwise been undetectable. And then here's a plot with the, on top we have the routine event detection, again from SeisComp3, where you can see in eastern Oklahoma, we have several quarry areas where we're detecting quarry blasts and labeling them as such. And then our augmented map here shows those events that are just, that wouldn't have been detected otherwise. And you can see that in eastern Oklahoma, we're able to detect events that wouldn't have otherwise been detected, but we also identify several more quarry blast events. And this improves our ability to sort of monitor the entire state because we have somewhat lower station density in eastern Oklahoma. Now, because we are a regional network and we want to have the most verifiable events, there's somewhat less than 1% of events are unconfirmable by analysts. Either they are actually false positives, or they're simply too noisy to be identified as an earthquake by a human. And so in those cases, those are likely small magnitude events if they are not false positives, and we just leave those alone, and we don't put them forward to USGS or add them to any of our state catalogs at that point. They just become, possible detections. They're not verified. This is important because that verifiable data as a regional network within the Advanced National Seismic System, all our detections are and locations and earthquake information, scientific products are distributed by USGS because we have authority within the state. And so it's particularly important that this information is verifiable. So that routine looks like this. So we run it daily when the UTC day ends. Those individual event files are added into SeisComp3. We strip away the event information and add the origin, and then it automatically identifies it as an event and gives it an event number, which is sort of internally trackable. And then the analyst will work that event, just like any of the other real-time detected events. And then that makes it onto the state and USGS catalogs. So it's particularly flexible. So one of the things we wanted to just to show as a sort of possible case study is this central Idaho earthquake, March 31st, 2020, magnitude 6.5 in central Idaho. We ran easyQuake fairly simply. There's example scripts available in the GitHub folder, but that's really required is taking some of the driver scripts, changing some information, some regional information, what sort of zones you want to include, what time range you'd like to include for that detection time range. And easyQuake outputs a particularly rich and informative catalog, which then could be utilized for several kinds of different studies, whether that's relocation kind of driven studies, earthquake physics studies, other types of studies in which a robust catalog is desirable. We think there's an application for early aftershock identification. So for example, USGS produces an aftershock forecast shortly after large events, but those parameters that are in those Riesenberg and Jones equations, which are derived from Amori and an assumption of earthquakes as a Poisson process. In particular, the aftershock productivity value A and C. You can get a wide range of predictions for probability of having a magnitude 5 earthquake, say after a magnitude 6.5 main shock, depending on what A value you're using. So it's possible that actually, using machine learning in a very fast way could improve your determination of some of these A value parameters, for example, C value, P value, and even B value. And this is particularly the reason that after, an aftershock forecast is put out by USGS, they'll typically update it within hours or, within days of that aftershock forecast, because in order to capture the right variables that are going into this aftershock productivity equation. So this is an example of the range of A values that might produce the probability of having a magnitude 5 earthquake as an aftershock of a magnitude 6.5. And then obviously C value is that sort of delay time variable. And you can see there's quite a wide range of forecasted probabilities depending on whether you're getting the right C value. So we think this is a pretty flexible, not just for our use case at being a local regional seismic network, but also has some research potential. And we've tried to make it pretty seamless and easy to install on systems that have a GPU accessible. So it should take, this 6 lines or less. If you have some trouble getting started or want to think about possible applications, please feel free to email me. You can cite our paper here, which will appear in SRL shortly. And then finally, in the future, we hope to expand this package, this Python package, to start producing sort of near real-time detection capabilities. And we'd like to expand the modularity. So envision the flexibility of installing or telling it you want a different picker, or you want a picker, you want to use the GPD picker, but on a model that you've trained. We envision a future where there's direct HypoDD relocation capability, or direct capability with hash to compute focal mechanisms, rather than just what we have now, which we have submodules that produce those output files for running those programs externally. And finally, we'd like to do some plotting and some statistics within easyQuake modules, which isn't quite fully realized at the moment. So anyway, thank you very much for your attention, and I hope to hear from you in the Q&A session. Bye.